vector of error terms, we know it's n by 1, right? So this should be n by 1. Indeed it is. Look at the two outer numbers, they tell you what the dimension is of that. And the two inner numbers should match if you can multiply these two together, if they're conformable, and they do match, so we're fine at this stage. Okay, so into the second part of the proof, where we can now, in a position, since we've got the expression for the residual vector, we want the variance of this thing. So we take the variance, you now use the variance operator. Variance on the left hand side, we take the variance on the right hand side. Let's call this thing here A, so simplify, otherwise my kind of working looks cumbersome. So variance of AY, where A is that thing. Now using the result of matrix algebra, since A here is something that's constant minus h, and h is a function of the x's, which we said right at the beginning we're assuming fixed, so in other words same as constant. Using that result we know that this is going to be, this is a separate proof but it's one of these basic results, so I'll just write it down. Since A consists of fixed elements, since A, so we could say is constant matrix, matrix of constants, matrix of constants. Alright, so that's a result that always holds when we have a matrix of constants. But what is the variance of y? We can write that down now. It's going to be A. Under assumptions given, the variances being constant and the covariances being 0, we can gather it together to write sigma square I to the n. If you want a bit more explanation of that, let's just do it on the side here. Variance of y, taking it from the model, is the same as the variance of x beta plus the error term, but x is fixed. At beta, the parameters are fixed in the classical kind of statistics. So this is the variance of a constant plus a random variable, and we know that the result is that's not going to contribute to any variability at all. It's the variance of the error term. Okay. Remember, this is a vector, so in other words the variance of this thing will look like this. The variance of each of the error terms for each observation along the diagonal, and off the diagonal will be the covariances. So here will be covariance of error 1 with error 2, blah 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 blah, and we've just said all those covariances are 0 by one of the assumptions. So in other words, and since each of these along the diagonal, the variances are assumed constant, being equal to sigma square, that's sigma square, and sigma square all there, which you can take out, so that ends up being sigma square times a matrix of zeros except for one along the diagonals, which is the definition of our identity matrix with dimension n. Okay, so that's how I get from here to here, like that. Just these small things that I can fill in the gaps, because otherwise if I don't do that, it's pointless doing this video. You could just get it straight from the textbook. Okay, now that is a constant, is a scalar, it's 1 by 1, just a number, and using matrix algebra again we know that it doesn't matter if we pull that out. A times identity times A. Now any matrix times that identity is itself, so that's simply going to be A times AN is A, or you could do it the other way around, A identity times A dash is A dash, so you can get this. Now we're going to be able to show, we can substitute in now for A. Let's do that. This H matrix is very, very important, and it has some desirable properties. So why don't I just quote those properties before I use it. This H matrix, indeed the matrix I minus H, they're both orthogonal projection matrices. And orthogonal projection matrices satisfies two conditions: one, that they're idempotent, and two, that they're symmetric. Symmetric, we know what that means. It means that if you take the transpose, it's equal to itself. That's symmetric. Idempotent means that if you take it to the power of any number of power, it's just equal to itself. So h squared equals to h cubed equals to h, so h to any number, let's say h, a, any integer, is itself, and that is what we call idempotent. And this holds for what they call orthogonal projection matrices. Okay, that's a bit of jargon which you don't need to know. Showing this is very simple for our case. Showing this is also very simple, so I'm just giving you the result here. Right, so if you multiply, so I've just told you that since this is also a orthogonal projection matrix, this thing times this thing is going to be itself. In other words, sigma square I minus h. Or if you want to do it in terms of h, just multiply it out in the usual way, multiply out the brackets and apply these two results. And what I've written here also holds for this, because they're both projection matrices. So would you believe it, we are pretty much done. But I want it for each. This is a matrix, n by n matrix, I hope you see. Right, because it's scalar times this thing, which is n by n. So it contains the variances and covariances. If we want to extract out the variance from this, which is what we're asked to prove, it's easy to extract out the variance because it's just to write the stuff on the diagonal. So we can set the variance of the variance covariance matrix of this residual sigma square. If I start to do that, this here, 1's on the diagonal, 0 off the diagonals, definition. Now this thing, that's where you're going to see the notation, using matrix notation, set row 1, column 1, h1, row 1, column 2, and so on, row 1, column n, okay, diagonals h2, 2, h, n, n, because n by n matrix, okay, h, 2, 1, okay, h, n, 1. We want just the stuff on the diagonal. So what we can see, if we use the diagonal of here, which will be equal to the variances, it's going to be sigma square for the first one, 1 minus h1, 1, and that will correspond to the variance of the first residual, that, and you can see that the second one is going to be the same. Take second row, sigma square 1 minus h22, and this will be the variance of the second residual, and so on. So I hope you can see then that is the proof. That's the proof. Finished. Okay. Great. That wasn't too bad. Another time, for another video, I will show you that this here, the leverage term, take the value between 0 and 1 inclusive. Okay, which makes sense because remember, if we don't have any restriction on the h, then you could see that you might have negative variances. This times something which could be negative, which wouldn't make sense. Alright, so catch you around.